mic for now. I think,
Does the mic work?
and I want to
Does the
welcome
mic-
you all this afternoon to the 2019 Stanford On The Moon Alumni Reunion Conference. Well, Stanford alumni
should be there.
all are welcome to
It doesn't
the
work,
Stanford
though.
community and friends
It's
of
right
Stanford.
there.
Our theme,
Oh, maybe it
well,
works.
I'm very happy to be back again this year in the physics department. I'm very appreciative of the physics department for again hosting us. Last year we had a splendid event, maybe not even as well attended as we have today. It looks like just about all the different chairs are occupied. Last year the subject was First Women on the Moon, given Stanford's illustrious and distinguished accomplishments with 8 Stanford graduate women being astronauts. Our speaker last year was astronaut Henning, and we're very, very happy to welcome Tammy back this year as a attendee, as well as a commentator as appropriate. So, this year's theme is, well, let me just say that Stanford on the Moon originated during my 35th class reunion in year 2000, and the idea officially was articulated at the class panel discussion 2 hours after John Hennessy was inaugurated as the 10th Stanford president. We've had support from former President John Hennessy said Stanford on the Moon, good idea, keep it up, so that's what we're doing. So this began almost 19 years ago. We're into our 20th year. It's a long-range project. We don't know when Stanford will have a center on the moon. Whether it will be an extension of the overseas studies program, way overseas, which had an enormous impact on my Stanford career and my Stanford years, the experience I had at Stanford in France. In a sense, it reorganized after our 2 terms a 10 classmates mission made out to the then Soviet Union in 1963, 20 years old. And it was that kind of spirit of exploration and adventure that led to the same spirit considerations for this even more ambitious venture to see that Stanford has a center on the moon. That as we were going back to the moon, a big change from last year, the idea of First Women on the Moon that we began, I believe, first articulating during the 2016 presidential campaign is now, at least policy-wise, a reality. Getting the necessary support and funding for the Artemis program, as it's now known, is a challenge that I had a chance to talk with the NASA Administrator Jim Bridenstine just a couple of days ago during the International Astronautical Congress, which is quite a meeting in Washington, D.C. In fact, it's just concluded. And we'll see. I'm concerned that another initiative led by the administration, I'm concerned that it succeeds this time. And in a short while, it's very dramatic change since last year, 4 or 5 years. Exactly right. Women to the South Pole, women, and men, of course. The subject of our meeting this year, Antarctica and the Moon, the 7th and 8th continents. And I think there's a very strong analogy at work here. 100 years ago, at the beginning of the 20th century, there was a great competition. One of the main topics of the day was the great race to Antarctica to see who would get there first. And as we know, the Norwegian explorer Amundsen got there, I think, 5 weeks, 7 weeks before the British explorer Robert Falcon Scott. And the competition was over. Scott's team had tragedy on their way back. But nobody went back to the South Pole for 50 years until 1957 during the UN International Geophysical Year, the same year that Sputnik was launched. 50 years. And since that return to Antarctica in 1957, we now have a situation where there are 50,000 people a year going to Antarctica. And I think the same metrics, the same dynamics may be at work for the moon. A great competition 50 years ago to the moon, it was won, and the USA hasn't touched the moon since, not at all. It's rather mystifying. Maybe now that all of the American population, not just 50%, are represented in the return will succeed. That may be an issue. So we're going back. It's not just an American goal. All the major spacefaring powers and some of the smaller ones, such as Canada, Korea, or South Africa, as well as America, Japan, China, India, Russia, Europe, have interest, strong interest, and in particular, there's a wide consensus that the asset-rich South Pole is where the greatest probability of human settlement developing is. There's a widespread consensus for the South Pole. So South Pole of Earth, South Pole of the Moon. 50 years from now, or maybe less, there may be 50,000 people going to the moon a year. And I think that's what would be necessary for a Stanford Overseas Studies program. Can I ask if you're all familiar, how many people are familiar with the big Overseas Studies program? It's a wonderful, wonderful program, and hopefully will continue for another 50 years. I think it just celebrated its 50th year anniversary. Well, it's just over 60 now. So that's the analogy, and that's what we're looking at. It's long duration. People say when? I say, well, sometime in the 21st century. I think that's a fair bet. The moon in astronautical and space community circles has been frequently referred to as the eighth continent for human endeavor, for settlement, for commerce, for civilization. And hence the theme, the seventh and eighth continent, Antarctica and the moon. We have, after fairly extensive explorations through the university schools, we found that without doubt we're located in the leading venue for interest in Antarctica here in the physics department. Several of our distinguished speakers are astronomers, including astronaut Jernigan, who studied astronomy as well. It seems well suited for Antarctica, the high and dry location. And we're hoping that there'll be interest in Antarctica throughout all of the 7 Stanford schools of sciences, where there has been quite a lot of research, not currently, but in years past and hopefully in the future, law, medicine, engineering, education, business. And so why don't we get going? The program includes the director of the Kavli Institute, Dr. Risa Wechsler, who will be leading off in just a moment with some general description, explanation of what Kavli Institute is doing up the road in the slack there, and a physics professor here who's led I don't know how many missions to Antarctica to do astronomy with the cosmic microwave background telescopes, BICEP telescopes that have been there. And maybe either Dr. Wechsler or JiaBin Huang can talk about the 10-meter South Pole telescope and the BICEP telescope, which I understand are very closely sighted at Antarctica. Roger Romani, whose very eclectic knowledge, it seems to be of most everything of interest. Roger has some general perceptions to share with us briefly, and so that we're not all from physics department here a Stanford On The Moon supporter, a donor to the Endowment Fund, which I'll talk a little bit later about what Stanford On The Moon has done and what it intends to do. Henning Roedel from the engineering department, civil engineering, will talk about similarities, rethinking construction, rethinking construction for Antarctica and the Moon. So that's our program, and to start it off, it's my great pleasure to welcome you all on this afternoon, a big crowd, and to welcome Dr. Risa Wechsler to talk about Stanford in Antarctica via the Kavli Institute.
Not very well. Hopefully this is going to change.
Okay, so I'm Risa Wechsler. I'm the director of the Kavli Institute for Particle Astrophysics and Cosmology. It's a little bit of a mouthful, so usually we just say KIPAC. KIPAC is actually a joint institute between Stanford and SLAC. We're about 16 years old now, so we have faculty in both of these two buildings here in the physics department and another building up at SLAC. And it's a really exciting institute because we really have the resources of the University of Stanford, but also we're able to do big projects at the National Lab, which is really exciting and actually is going to be relevant for work at the South Pole in the future. So we're about 200 people, to about 20 faculty, 30 postdocs, 40 graduate students, and it really kind of encompasses the whole astrophysics and cosmology effort at Stanford and SLAC. And we work on, kind of everything in the universe. We're interested in how the universe began, how it evolved over time, what it is made of, the nature of dark matter and dark energy that we think dominate most of the material in the universe. We're also interested in all of the things in the universe, stars and galaxies and black holes, and in particular also the things that black holes do to their whole environment and the ways that we can see them in different ways. So it's really it's a big span of all of astrophysics, and one of the things that we do at KIPAC is really we work on big projects. Having a lot of technical capabilities here at Stanford and at the lab allows us to do really exciting big things, and this is not all of the things that we do, but it's some of them. One of the things we're doing right now is building the biggest camera that has ever been built. It's a 3.2 gigapixel camera. It's being built in our labs right now at SLAC, called the LSST, Large Synoptic Survey Telescope. And that telescope is going to start taking data in a few years. It will survey half the sky for 10 years. It not only takes a very deep picture, it actually takes a movie of the universe, because it goes back to the same part of sky essentially every 3 days. So you're able to see all kinds of interesting things. We expect to actually discover all kinds of new astronomical objects that change with time, all the way from things in our solar system to things that are 12 billion light years away. One of the other projects that we do here, primarily here on campus, is we're looking for planets that are in solar systems outside our own. Professor Bruce McIntosh is the PI of an instrument called GPI, which has recently found 300 planets in external solar systems, and actually started to take really fuzzy images of these few pixel images of these planets, and it's really exciting. We're also doing lots of different ways to look for dark matter, both in the lab and in the sky. And we're also involved in big projects to map out all of the galaxies in the universe. Now, the projects that are most relevant to Antarctica are the projects in the cosmic microwave background, which you're going to hear more about from Qiaolin, so I'm only going to say a little bit about it. But this is a really exciting research program, which I think really has kind of two main aims. One is really to search for the earliest moment of the universe that we can get information about, to actually try to learn something about the energy scale of the inflation moment of the universe. And the other thing is really just to make this very precise map of the universe about 400,000 years after the Big Bang. And not only we can look at what that map is, but we can see what the intervening matter did to it since it was emitted, and that gives us some information about how structure formed over the universe. So it turns out that the South Pole is really the best place to do those kind of experiments, and so you'll hear more about that from Qiaolin. Just very briefly, these are most of our key faculty, and you can see many of us are both either at Stanford or at SLAC, or sometimes both. Lots of great people, all the way from people building the most sensitive detectors in the world to the people doing theoretical calculations and simulations and observations of the sky. One of the really wonderful things about KaiPAK is that we train postdoctoral fellows here, and they are really kind of the energy of the Institute. We have about 33 postdocs and research scientists right now. These are some of our fellows. They again are engaged in all of these really exciting projects. They work with undergrads and graduate students as well, and some of them definitely do go to Antarctica to work on CMB experiments. I just thought I would spend 1 minute sort of giving you a few science highlights. These are just news articles from the last year. For KaiPAK, I already told you about this analysis of planets outside our solar system. KaiPAK was really involved in an exciting project called Fermi. That was also a space telescope that we actually built up at SLAC. And Fermi just had its 10th anniversary, and so it's done lots of things, essentially made this beautiful gamma ray map of the sky, and this year discovered some new record-setting gamma ray bursts. You can see here that we also are involved in the LIGO project, which discovered gravitational waves. That was partially enabled by really key technical contributions in lasers and also control systems here at Stanford. And we're also using galaxy surveys to make maps of the universe as large as we can, and really trying to understand if we can map out all of the galaxies to figure out where the matter is, and figure out whether we can test at much higher precision our current understanding of dark matter and dark energy. So in the last few minutes, I thought I would just show you, could we get the lights down for a second? I just want to show you, oops, should be going. Is it possible to get the lights in the front?
Yeah, there's a...
Yep. So this one?
No, to the left. There you go. Other side, probably.
Okay. Okay. So this is one example of what I do in my group. What I'm trying to do is simulate the entire universe. Wonderful. Okay. And so what you're looking at here is just a random realization of some piece of the universe. And what you're seeing here is how structure forms. The span of this movie is about 13 billion years. Okay? And we actually start, this is a really beautiful physics problem because we actually have a really good understanding of the initial conditions through the map we make of the cosmic microwave background, which is what you're going to hear about from Qiaolin. And that really tells us what the universe looks like very early on. There's places where the universe is a tiny bit more dense and a little bit less dense, and then we put that in the computer, turn on gravity, and this is what happens. What you're seeing here is how structure forms in the universe. You start out very smooth, you get more clumpy. In the places where the universe is pretty dense, you're finally able to form stars and galaxies.
Is that based on actual data?
So it's based on actual data in the following way. The initial conditions of the movie are actually based on real data. on this is sort of a random realization of part of the universe that could exist based on the measurements that we know. And then it is also tested with data. After we make this movie, we can make predictions for where all the matter in the universe is, and then we can test that with surveys. So this is one example of the data that does that test. This is data from the Dark Energy Survey, and what we've done here is actually use the shapes of about 200 million galaxies. Those shapes are slightly distorted by something called gravitational lensing as they travel through matter in the universe along the line of sight. And this picture, it tells you where all of the mass in the universe is on about 1/8 of the sky. And so we can make predictions for what this should look like using the movies that I just showed you, and then test them with these kinds of measurements. So that's all I wanted to say, and what you'll hear now is more about that cosmic microwave background and what it's like to do research on that in Antarctica from Challenge. Yeah.
Okay, I don't have any slides. No one quite know what the setting would be. I thought it's a roundtable discussion. But I would have some pictures with me. But my name is JiaBin. I'm a professor here, physics department, as well as SLAC, member of KIPAC. I'm an experimentalist. Like Risa said, my main project is a BICEP telescope at the South Pole. What we're doing partly is to supply the initial condition for Risa's simulation. Somebody asked whether that was based on actual data. So in terms of statistics, it's entirely based on data. And the measurement of that data came from cosmic microwave background radiation, which is essentially, you can think of it as a firewall in all directions. So as you know, light travel at a finite speed, so there's a look-back time, meaning things that you're seeing now were emitted, giving off these radiation a long time ago. At some point, you reach not the edge of the universe, but rather the beginning of the universe with that look-back time concept. And so that's why you look everywhere in any direction, your line of sight hit this firewall of radiation. Now that's shifted, as the universe expands to the microwave region. This sounds very strange, but as an experimentalist who built instruments, so if I just build an instrument at 2 millimeter wavelengths, and you looked out, you see this stuff. It's just as real as the sun, as the stars. Okay, it's really out there. And it has this tiny fluctuations that we measure that describes the initial condition, this quantum noise that was basically put in at the very early epoch of the universe. And Risa and company took that information and simulate what would happen when this noise, cosmic noise, as density fluctuation collapses under gravity to form stars and galaxies and so on. Okay, so that's what we do. That's a very, very rough version of what we do. We've already measured this density fluctuation extremely well. Now what we're trying to measure is this particular imprint in the polarization signal of cosmic microwave background. That would be the imprint of primordial gravitational wave that was created with Big Bang. Okay, so Risa mentioned something about inflation. So that was the physics mechanism that's related to Big Bang. So is Big Bang a one-off thing? There was this bang and nothing to hold on before, and that's just a one-off. Or was it described by a physics process? Now we think this is a physics process. Happened once, it could happen elsewhere, it could happen multiple times if it's described by a physical process. That's why we think, inflation is not just, theorists, funny ideas about the beginning, but rather we're trying to even include the beginning in the realm of physics. Okay, so that's the that's the difference between what we call Big Bang and inflation theory. So this thing, particular thing, primordial gravitational wave, that we study as evidence for Big Bang is in the polarization state of microwave background. And like I said, microwave background peaks at 2 millimeter, 3 millimeter, or about 1 millimeter wavelength. So this is also a wavelength that's strongly absorbed by water. So that's why we go back to South Pole, really. Because South Pole is the driest place on Earth. You probably don't know this. You probably thought Sahara is drier, or Mojave Desert. But in fact, because of the extreme climate, Antarctica is the driest place on Earth. Because all the water vapor is frozen on the ground to form that continent, basically. Okay, so there's very little supported water vapor in the atmosphere. And that's why we go there. So the atmosphere is extremely transparent in the wavelength that we're interested in. Well, there is indeed a lot of similarities between Antarctica and the Moon, now that I know Antarctica is the seventh continent and the Moon is the eighth. So first of all, when I landed in Antarctica for the first time in 1998, I thought, oh wow, this is really like a different planet. So everywhere I look is this, landscape that I can't, there's nothing basically, just complete whiteness. And you have to survive in this building, they're all blue, with, windows, and you look out, you see this, exotic landscape. And it does give you a feeling that, you're an astronaut and you're just surviving on a different planet. And if you go out without proper gearing, you'll die in 5 minutes. So that part is also similar. In space, it's 5 seconds. Right? Another thing is, there's great science to be done in Antarctica. That's why we go back to the South Pole after all these years. There's the cosmic microwave background. There's another group, prominent group, using the ice itself to detect neutrinos coming from supernova explosions and so on. So these two are the main science objectives of South Pole. There's another thing about South Pole that, at least for me, was a big challenge, because the South Pole Station is only open for 4 months per year. You have to plan your project extremely precisely. At this stage, you have to ship your cargo, all 45, big crates of them, to a certain, port in California, so that the logistic people can ship them to Pole and so on. There are these complicated, and you have to get out on the plane and finish all your project and leave your experiment working there by February 14th every year. And that's been the case for the last 20 years. So you have to do extremely well logistic planning for any Pole projects to be successful. I know it's not as hard as going back to the Moon, but for me it was a pretty big challenge as a professor here, when I started. Another thing that you remember was the most famous picture of the Earth was taken by an astronaut. Do you remember that picture? So, what Earthrise, right? It was Earthrise, Apollo 9 or something. So in Antarctica, you can also learn about our planet very well. Even though we've done great science, astronomy, neutrino, I personally think the most important discovery in Antarctica is, do you know what I have in mind? Is these ice cores. So people drill into the ice core, get it out, realizing these bubbles encode the amount of CO2 in the atmosphere in the past tens of thousands of years. You plot CO2 as a function of time, you immediately see a man-made CO2 rise. I think that's the most important discovery in Antarctica. And just like going back to the Moon, you learn about the Earth. Go to Antarctica, you can also learn about the Earth. I'll take questions. Yes?
Hi, what is the length of the cores when you do the analysis?
So, okay, this is the part that I'm least familiar with.
Sorry.
But as you know, probably know, Antarctica is mostly sea ice. So the entire thing, the actual land is under seawater, under sea level. So the entire ice core, in principle, could be nearly 3 kilometers high. I don't know what the longest ice core is.
No, just short for it.
Yeah. And this was accumulated over, I say millions of years. But I got the impression that they can go back in time, in tens of thousands of years. And these ice cores were roughly 1,000 meters long. That was my impression. I think the longest one was taken at Vostok station. It's the Russian station. This is a collaboration between the European scientists and the Russian at the time.
Thank you.
Yes.
You mentioned being able to view the edge of the universe, or
Yes.
then you rephrase it, possibly the beginning of the universe. Do you take into account quantum physics and mechanics and the idea of a bendable universe, and is that part of what you are studying, or does that have any effect on your
We're
study?
based on our measurement on relativity, theory of relativity, which is now considered classical theory. So when you calculate the length, the time, angles, this sort of thing, we're all based on general relativity. So it definitely includes bendable space and all of that in there. But like I said, we think this initial noise that showed up as density fluctuation were put in there by quantum mechanics.
Right.
Could you describe in more detail some of the experiments that you're performing there?
Right. So in terms of cosmic microwave background, we have two big projects. So one is doing exactly, what Risa described, using the microwave background as, backlight to probe what's in between. So that experiment is a 10-meter South Pole telescope, and it has discovered thousands of clusters of galaxies that way. Because these clusters of galaxies are in the way between microwave background and us, and you can discover them as holes in the cosmic microwave background. Okay, so that's the 10-meter South Pole telescope. Our telescopes are smaller because we build our telescope to tailor the resolution of our telescope to match the primordial gravitational wave signal, which is a few degrees, like a few times the size of the full moon on the sky. And both telescopes use superconducting detectors operating at below a Kelvin absolute temperature. And just because of that coldness, it's super sensitive to any form of energy. And we scan our telescope back and forth to register the temperature on the sky and make maps out of it. Yes? Please.
I realize you haven't been to the moon yet,
No.
Yourself. But what do you think, based upon what you already know, the data you already have, what could you do in terms of the study of the background radiation from the moon that you don't think you can do for now?
Well, it will be a dream project.
Why that? Why?
Because, like I said, during my talk, the reason we went to Antarctica, to South Pole in particular, was because of the lack of absorption from water in the atmosphere. And on the moon it'll be better, but we'll take orbit, not necessarily going to the moon. There are other things better on the moon. Like people talk about building big radio telescopes on the moon, so that those are expensive, but it'll definitely be much more capable than what we have now.
Okay, one follow-up. Now, I may not understand, but from my reading, it's my understanding that the initial quantum fluctuation
Yeah.
is assumed or known, I'm not sure which, to be random. So in order to have all of the structures of the universe and everything that's happened, it had to leave randomness.
Yes.
What is responsible for that?
Yeah, so we have a very successful theory based on inflation to predict the form of quantum fluctuation under that paradigm. So if inflation predicts initial fluctuation of certain spectral shape, and if we take that spectral shape and evolve it to microwave background epoch, it agrees with what we see in cosmic microwave background precisely. And we take it further to evolve it to the galaxy level, clusters of galaxies level. It again agrees with what we see in the distribution of galaxies.
So by the word inflation, I think what you're saying in lay terms is that the very fact of the expansion leads to the
It's a
non-random.
little bit quantum. It's a little bit more complicated than that. So we think the ground state of the initial field that was responsible for inflation has vacuum fluctuation in it.
To
And
begin
then-
with, from
to begin
moment
with,
one.
just from quantum fluctuation, any field has quantum fluctuation. It's not just zero, even in completely empty space. Electromagnetism is not completely zero anywhere, even in vacuum, because of quantum mechanics. So any field will have that fluctuation. So during inflation, that quantum fluctuation gets inflated into a classical fluctuation, and that goes into infinity. So there was a question. You have a question? Anyone? Okay. You have a question? Somebody have a question? Okay. Please.
Hi. So, how do you think the field of gravitational wave astronomy will affect your research?
So the type of gravitational waves that we're interested is fundamentally different. Well, I mean, in terms of physical entity is no different than the classical gravitational waves that are being studied by LIGO. Okay, so they're the same sort of wave, but the wavelength that we are interested in is vastly larger. So it appears as a frozen wave, if you will, on the sky, not a modulating, propagating wave like you might be familiar with. And it was generated by what we think quantum mechanics during inflation. So the nature of the mechanism of the generation are quite different. Okay, whereas the type of gravitational waves that LIGO probes is coalescing black holes, neutron stars, and so on. Yes.
At any point in time, how many different research projects are going on at this 4-month period of time at the station?
There's quite a bit, but the biggest ones are these neutrino projects and cosmic microwave backgrounds. So these are the flagship projects that has generated pretty substantial results. There's also the atmospheric studies, chemistry. There's glaciology. There's this drilling of ice core. And what else? So there's infrared sky studies and so on. But the big ones are cosmic microwave background and neutrinos. Yeah.
You were talking about the ice cores and the CO2 and how you can
Right.
determine CO2 levels in our atmosphere over the
Right.
course of millions of years. And how exactly does that correlate with what you're studying in terms of these wavelengths, and how are you applying the data to what you're studying? And I think you touched on it. I didn't.
So fortunately, the CO2 level hasn't risen to the extent that interfere with our experiment. But we're definitely aware of that. And like I said, occasionally, people come in, have a drilling campaign, get an ice board, and take it back to Colorado for analysis. But no direct correlations.
Okay.
Yeah.
So are there any advantages to the South Pole for looking for exoplanets? And are there any advantages to looking for exoplanets on the moon?
Turns out South Pole is not a great site for optical visible astronomy because of this pretty severe immersion layer near the ground. So there's a lot of turbulence from that. However, we also know this. If you can build a tower that's 200 meters tall, it's going to be the best site on Earth. But it's pretty inconceivable to have a big telescope on a 200 meter tower to get above the turbulent layer. But it's not very practical.
Would there be advantages on the moon for looking for exoplanets?
Again, atmosphere is the enemy for astronomy, so yes. But I think there are other reasons, scientific reasons to go back to the moon than doing astronomy, because it's very possible. All right, thank you.
Well, thank you very much, Dr. Wechsler, Risa, and Dr. Cole. You got a real top-notch introduction to advanced astrophysics. And before I go further, is the chair of the physics department, Shami Kapfu, with us this afternoon? I thought he would be. I would like to introduce him and express our thanks. And I just wanted to fill in one thing. My work at this time is based in Hawaii, which is a frontier of astronomy, at least maybe the frontier in the northern hemisphere, whereas Chile, and even more so, Antarctica is a frontier of astronomy in the southern hemisphere. But we've been pursuing a project to do astronomy from the moon, for quite some years, and I think we're getting close. I think it will be one of the first activities when people do go back to the moon. There are quite a few advantages that I won't go into right now. The South Pole is where we're testing we put our instruments. And again, we're not too far away. There is, in fact, astronomy being done. Has been done for 5 years continuously now. On the moon, on the only first lander to return to the moon in 40-something years, the Chang'e-3 China lander in the 40 degrees north has a 15-centimeter ultraviolet telescope on it. And Chang'e-4 on the far side of the moon, which you probably heard the landing was earlier this year, is doing some of that very low frequency radio astronomy that is very promising and the big advantages of the moon will be on the far side. And Professor Kuo talked about some of the various researches being done, some by Earth Sciences, and there's, I think, some biology as well as glaciology. But we are looking for a cross-disciplinary, across the educational spectrum of interests and activities in Antarctica in the future. Again, with the hope that Stanford, a Center for Stanford in Antarctica may be a precursor, an analog to a Center for Stanford on the Moon. And with that, I'm very happy that Professor Romani is with us and perhaps has that broad, eclectic view of other interests and possibly other researches and activities in Antarctica. So with that, I'd like to welcome Professor Roger Romani.
So if you look at your little program, you notice that there's a title there of Future Life in Antarctica. Wow, when I saw that title, I didn't quite know what to say, except that following Chow Lindsley, you've noticed that we see that human beings are pumping CO2 into the air. And so my prediction for future life in Antarctica will be palm trees, but 6-month-long days and nights, so maybe not all that great. So what I would like to do is tell you what I think the real title of this talk should have been, Discussions with Steve. So what he would like me to do is to share a bit some of the things that we have talked about over the past couple of years associated with Stanford on the Moon and more recently with Antarctica. Let me tell you a word or two about what I do and why I'm here, and then I'll just share some of the things that we have discussed in the past. I speak about the Moon and Antarctica from a position of great interest but no special authority. And so when I say discussion, I think it will be a discussion with you as well. I'll have a few comments to make, and then I can take questions or we can just discuss these topics. So I've been here at Stanford teaching for about 30 years now. I am an astrophysicist as well. My specialty is black holes and neutron stars, compact objects. And so I kind of work at a different regime of the spectrum, not the lowest energy photons we see, but rather the highest energy photons. And some of that work, not as much as the microwave background, does take place in Antarctica, but it is not the mainstay of what we do. Most of what I do is actually from space, although I use ground-based telescopes quite a bit as well. I've been here 30-odd years, as I say, and we was part of the team that a small group of us got together and started this thing we now call KIPAC, and so it's really extended the reach of astronomy in Stanford appreciably. Some of you folks who may have been here quite a while ago may remember Stanford does not have an astronomy department. It has an astronomy program, but it's a subset of physics. It was a relatively small endeavor for many years. When I got here, there's only 3 or 4 of us really doing that kind of stuff. But it's expanded greatly. As you saw from Risa's slides, we now have a couple dozen folks that are involved in astrophysics of one sort or another. So it's such an exciting field that Stanford realized it needed to be a part of it, and it's kind of grown up accordingly. I think you can sense that same sort of excitement about space physics and the moon in particular growing in the community. And part of that sea change is really due to the fact that our return to the moon is no longer a geopolitical stunt. It's a return that is driven partly by economics and partly by curiosity. The idea that we now have commercial access to space, which will be growing in its impact and shrinking in its cost, I think is very important for the sort of discussions that we've had here. In the same way, as Steve mentioned earlier, I think that's the analog of what happened historically in Antarctica is a good analog there as well. Originally, it was a great geopolitical, if you will, quest, the race to the pole. It became, in this intermediate period where we're largely living now, a scientific enterprise. but is moving into a human, let's even call it touristic enterprise. And that same sort of transition will inevitably happen in space as well. The problems are harder, the timescale is longer, but we, I think, as one of the leading institutions of both scientific research and human exploration, we at Stanford really want to be a part of that endeavor. And so I think what Steve's doing for us is helping us focus our thoughts on what it takes to make Stanford have a significant role in this new era that's coming, to position ourselves to be major players in the era of human beings, general human beings in Antarctica and human beings on the moon. So let's see, so I've got a little bit of history here, so let me make a few more comments. You've heard already that the reasons that, let me talk first about astrophysics and then the more general topics that Steve wanted me to cover. You've heard that from an astrophysics perspective, we go to the South Pole because it's high, dry, for half the year, dark, and remote. Well, the moon, after all, is even higher. As we heard, it's even drier. And for half the year, it's even darker. But it is awfully remote. And so the challenges are severe, but the payoff can be high. Now, another reason that you go to Antarctica, as we've heard, is because there's a lot of ice. What water there is in the form of ice. And you've heard about the projects that involve the dryness, that's the microwave background, and to some degree 10-micron observational astrophysics. But the ice itself plays an important role, as you've heard. The project called IceCube, which is drilling large strings with hot water, drilling large strings in, tunnels into the ice and dropping in strings of phototubes, and using the flashes, the scintillations of light that occur when high-energy neutrinos, or the particles really generated by high-energy neutrinos, come racing through that subantarctic ice over this 3-kilometer depth. They can use that volume as a detector, a sensor, to measure the impact of neutrinos. Now, this is particularly powerful in Antarctica when you're looking in the northern hemisphere. You use the Earth as a giant filter to cut out everything else, and so things that are coming up from below, the only things that can get through the Earth are neutrinos. When they convert in the ice and you see the flash of light that points back into the northern sky, you say, I've really got something. So that's probably the second major endeavor scientifically that's going on in the astrophysics regime there. These things are going to continue. I have a particular interest in those neutrino events because one of the things I work on are the supermassive black holes that power cosmic sources called blazars, typically is the technical name. They're black holes with jets of relativistic particles shooting out, and as those jets of relativistic particles propagate, they give off gamma rays. So I was part of the Fermi team that looked at the Gamma Ray Space Telescope, where we discovered tens of, well, okay, we're up to about 6,000 of them now, but it's going to be about 10,000 in total of these blazars across the sky. But it turns out those same machines sometimes accelerate not just electrons and positrons, which give off the light we see, but hadrons. That would be protons and related particles, and in turn, those produce neutrinos. So it's very likely that some of the neutrino events we see from deep under the ice in Antarctica are directly related to the sort of objects I study, the very high mass, very powerful black holes out in the distant reaches of the universe. And so we've had some interaction with the folks that are studying the very rare neutrinos to connect them with what we do in astrophysics. There's another project, in thinking of future science in astrophysics, that a team of us here are involved in. You heard a word or two about the LIGO program that Stanford played a big role in. What our real role was there was mostly over in applied physics, to be honest, and our contributions were twofold. We had Bob Byard was really the leader of the laser program that built the first lasers for the LIGO machine. And so that powerful laser, which is bounced back and forth to do the sensing, is really an outgrowth of the laser physics here at Stanford. Closely related to that is another group that does a lot of control theory and a lot of mechanical isolation is their expertise. And to find gravitational waves here on Earth, it turns out to be very important to make sure the mirrors that we bounce those lasers off of are isolated from any other disturbance. The very delicate assemblies that are used to hang those mirrors and keep the vibrations of the Earth, seismic and otherwise, from interfering with them, were also developed here at Stanford. And indeed, the future generations of those isolation systems, which are going to be used for LIGO upgrades, are still being worked on, mostly over in applied physics. So we played a big role in that. But we're looking ahead to what will happen next. LIGO turns out to be particularly powerful at measuring waves, that kind of gravitational waves that oscillate at the kind of frequencies that if you put it to a loudspeaker, you could hear with your ears. Kilohertz. And it turns out that that's the characteristic signature of objects that weigh a few times to maybe 10 times the mass of our sun, colliding and merging. Typically neutron stars and black holes, so that's why I care. But it turns out that they're not exceptionally exotic objects. It also turns out that LIGO, that merger, that chirp that comes out to audio frequencies, which LIGO can see, happens only during the last few seconds of these objects' lifetime, when they're just about to coalesce. So one of the things that I and my colleagues here have been interested in is trying to look at both lower frequencies and catch these events earlier so we can study them in some detail. When LIGO sees something, it's all over in 10 seconds or less. There's nothing else left there. But if we can find these things a year or more before that final catastrophe, then we can take the world's suite of powerful instruments and turn our sights on where and one of these events is going to occur and really probe the physics of what's going to be happening when these two black holes get together and annihilate, or two neutron stars collide and make the heavy elements which, give us our gold and our platinum and all that other good stuff. So our chance to really study the detailed physics of these objects involves doing something different than what LIGO does. And one of the tricks being developed by some of my colleagues here is to use, instead of mirrors to reflect light back and forth, to use atoms, individual atoms. Well, now, that seems at first a little bit bizarre. How would that help you? The point is that individual atoms, if you can use them as the reference source, the thing that provides the reflection for passing the light back and forth, is they're relatively cheap, and so you can drop them. You see, to make something completely isolated from interference from the surface of the Earth, it would be great if you didn't connect it to the surface of the Earth at all and just let it fall in a vacuum. Okay, well, the mirrors that LIGO uses are very, very, very expensive. Many tens of thousands of dollars each, many hundreds of thousands of dollars each, and you cannot afford to continuously drop a whole series of them. Atoms are relatively cheap. If you could make the atoms act as the mirrors, you can just drop them willy-nilly, and so you'll have isolated reflectors. So atom interferometry is one of the key schemes to developing a system that can work like LIGO, but at slightly lower frequencies, so we can catch these merger events before they finally collide. So that program is starting here. The physics is actually being developed over in the next building over in Berrien. There's a 10-meter tall tube in the basement where atoms are not just dropped, in fact, thrown up from the bottom, come up to the top of their arc and come back down. And while they're free falling, they measure the property of those atoms. The idea is to essentially use those things as mirrors and eventually bounce laser beams back and forth to reference them and therefore search for gravitational waves. 10 meters is not long enough. How can you go further? Well, there's a program just funded by the Moore Foundation, which is very exciting, which is going to enable them to develop a 100-meter prototype of this system. And that's going to be over in Illinois next to Fermilab in a relatively deep tunnel that was built there. But what you really need is several kilometers. And even better, you want these mirrors to be at certain sites several kilometers apart. So we have a little scheme here, which we've been thinking about, may not come to fruition yet, and that is to use the Antarctic ice as a site where you can make the said tunnels. You see, drilling through rocks is pretty difficult and pretty expensive. Drilling through ice is moderately difficult and moderately expensive. What you need is hot water. You need a lot of hot water. And once you've got hot water, you can drill your way down through that ice, down to depths, as JiaBin mentioned, of about 3 kilometers. So imagine now a sequence appropriately placed of these ice holes near the South Pole, drilled down to a depth of 3 kilometers or so with atom interferometers at the bottom, throwing the atoms up and having them drop back down, and then referencing back and forth between those. That could be a very powerful gravitational wave array, and I and my colleagues are talking about whether or not we can make such a thing happen. Okay, well, but I did promise I would say a few words about non-astrophysics things. And here, the role I guess that I'm taking is, Steve mentioned the Bing Overseas Studies program. For about a dozen years, I've been on the faculty oversight board for Bing. And so what we do is we review the different programs, the overseas centers, which I hope a number of you participated in. How many people were able to do an overseas studies program during your time here? Fantastic. I was very happy to go. I taught the Florence program some years ago, and I enjoyed that a lot. My wife is constantly trying to get me to go back. But, anyway, what we do is we review these various programs, and we shouldn't forget that in addition to the centers that many of you had some time at, which are typically quarter-long experiences for the students that go, we have the overseas seminars, which are 2 to 3 week programs. And they're less site-tied. So, but the effort that Bing would like to do is to try to cover the globe more completely by using the overseas seminars programs to fill in the gaps. You see, our Stanford centers are mostly in Europe, let's face it. As they were originally, many of them are still in Western Europe. We do have Kyoto, and we do have Santiago, and there's one in Australia. We are just about to open one in Hong Kong, but the recent unrest made that a little bit difficult. And then there's Cape Town, South Africa. But you notice that while we have a nominal foothold in the other 5 continents, number 6, or really Antarctica, number 7, if you will, there's no presence whatsoever. Now, it's not inconceivable that Stanford could play a role there. I think Steve has been thinking about, what if we had a real center there, you know, a place where students would go down regularly. I think it's going to be a while till that happens because of economic reasons. Let's face it, it's not cheap to go to the pole. It's also not as, when you're acting in loco parentis, as we are here in the Big Overseas Studies program, safety is really a priority. That's why we don't have an active center in Hong Kong this quarter, is because, you know, you worry about safety. And the pole itself is, as JiaBin mentioned, a harsh environment, not an easy environment. So an alternative that could be conceived would be South African polar overseas visit. So you could imagine a ship-based program that could go to Antarctica and do some of the exciting Antarctic science that can be done at the edges of the continent. Glaciology, marine life, certainly, climate change. And there's another aspect that I think Steve and I talked a bit about that's worth mentioning. When you think about sending folks down to a remote site like Antarctica, you should think about the entities that you're sending, people. The way people interact in these environments is actually very, very important. And the kind of human interaction and psychological studies needed to make people work effectively in such confined environments is something that we need to pay more attention to. Now, I'm not the first to think of this. It's really been well known that the Antarctic expeditions are a great analog for the sort of experiences that people will have to undergo when they go to our interplanetary voyages. So probably not the moon. The moon is not so far away. It's a matter of days away. But if you're going to contemplate Mars, that's months away. And so the minimum time for any such expedition is going to be many months. Having a small group of people confined to a very small volume for many months at a time prevents a number of interesting psychological dynamics, which have been explored at length in the South Polar programs. JiaBin mentioned that it's only open until Valentine's Day. Well, yes, except for a small, stalwart crew of folks who winter over every winter. And the dynamics of the small number of people who are essentially isolated for 6 to 8 months of the year is something that's worth paying some attention to. Now, this has been well appreciated that you know, these kind of experiences are a good thing to study if you want to plan a successful expedition to extraterrestrial sites. I'm no expert in psychology. I can recommend to you, though, that if you're interested in reading about this kind of thing, there's a really fine science fiction author. I hate to mention that here, but he has spent a lot of effort thinking about human interactions in an extraterrestrial context. And he wrote a very famous series, a trilogy, about the human colonization of Mars. Red Mars, Green Mars, Blue Mars. This is Kim Stanley Robinson. In that series, one of the precursors to selection of the crew that was going to be on these long-term expeditions to Mars was to have a residency in Antarctica at one of these research stations to see how well they occupied this small space and how well they interacted. That's where the final selections were made. Indeed, he also wrote another novel called Antarctica. And all of this is based actually on some experience. Stan actually was able to go to the South Pole, not the South Pole, to McMurdo actually, as a part of the NSF-sponsored Writers in Science program. And so he spent some time down there, and he knows whereof he speaks when he writes about human dynamics in these environments. I think this is the sort of thing that people outside of the technical fields here at Stanford would ideally want to be involved in. I hesitate to mention it in this context, but you do know that we have a number of famous experiments about isolated folks with human dynamics. Everybody can think of the prison experiment.
Oh, yeah.
Hopefully it wouldn't go that bad, but we do have folks who I think would be very interested in studying human interactions in those sort of environments. And so I think if Stanford is to get involved in this, what we have to remember is if you're going to be sending people to these places, it's the study of people that is probably as important as the places as a site for study themselves. Let's keep that in mind. So while we may be the spearhead of expeditions or projects that first visit these places, the people doing astrophysics and cosmology, that sort of thing, ultimately I think it'll be the humanists or the people that are social interaction as their focus that will be playing the biggest role in studies that involve these sites. Final comment, I think related to the earlier comment I made about the economics of doing all this. When we go and do science, there are some cases in which having human beings there to do the work is pretty important. But in some cases, and especially as you get off the surface of the Earth, it becomes vastly economically more practical to have robotic presence there. And this is a place where I think Stanford can have a presence on the moon, and perhaps to some degree even earlier on in Antarctica, where students can be involved. They can be involved early because they can be participating in the research that takes place there without physically going. JiaBin had undergraduates involved in his program, working on projects here on campus that eventually helped the program down in Antarctica. I don't know that you've ever sent anybody south. Have you sent undergraduates down?
Yes.
Wonderful. Okay, so occasionally even that can happen. Now when we talk about going to the moon though, I think it's going to be probably, as Steve said, 50-ish years. It's going to have to be the point where Antarctica is now, that ongoing tourism is available but fairly expensive before we will even be able to contemplate sending our undergraduates to a site such as the moon. But well before that, we can have undergraduates involved in building robotic probes, working on instruments that eventually would go to the moon, thinking about science experiments that are based on a lunar site. And so their involvement in lunar programs, I think, can start early. And I think that's important, because while we ultimately are all interested in having human presence spread beyond the Earth, there are ways of making that motivated that involve the kind of things that we can do today at reasonable cost and with reasonably exciting science results to get undergraduates involved. So I think that's the comments that you wanted me to speak to, that general sort of stuff, and I'd be happy to maybe not answer questions, because again, as I say, I'm not speaking from great authority, but maybe helps lead a little bit of discussion. So I'll stop here and we can have a little give and take. Okay. Yeah, Tim?
So on the International Space Station, of course, people have been up for as long as a year.
Yep.
Now, the space station used to be a small volume. It's no longer a small volume, right, because it's grown to the size of a football field. But there is a lot of pre-screening, psychological pre-screening that goes on before those folks are selected. So I would imagine any program in Antarctica would benefit from some type of pre-screening process.
My understanding is they do, certainly for the winter over folks,
Yeah.
they
They
do.
do. So for the winter overs, they do. You have to pass the psych exam. And,
But it
they don't
depends
tell
on
you
the
how you
exam,
fail.
right?
But if you're going for the summer, you don't even pass the psych exam. And there are still failures after the psych exam.
Yes.
Well, it depends on the exam, right? So when I flew on shuttle, so my longest flight was 18 days. We can suffer through anything for 18 days, right? And so the psych exams were pretty cursory. I mean, you knew sort of minimized amount of information that you might want to provide so that they had a sense that you were pretty normal. But in fairness to the psychologists, they were only given a couple hours with us, right? It wasn't extensive at all. But for space station, they instituted a policy where the exams are much more expensive and people are observed in a variety of situations. And so it got a lot more serious at NASA when they started putting people on station where you might be up there for up to a year. So,
But even then, you could imagine evacuation on the timescale of a week if you had to. And by the time you go to the
well, there's
moon,
no
it's-
right because you have a Soyuz, right?
Right, so
Docked
you can
to the
get out,
station,
yeah.
so you could absolutely. That is more thought of as there's an engineering problem, a technical problem, not a medical problem, right? Not a psychological problem.
Right.
Not that it couldn't be used for that, but.
Yeah. Well, I mean, they've had problems with winter rovers having challenges, psychological challenges, and there you couldn't get them out on the timescale of several months, so it's pretty bad.
Yeah, that would be tough.
No, the moon's not that far away. I think it doesn't change that paradigm dramatically, but
Yeah, but you
Mars
have to
certainly
have
does.
some sort of space asset, right, ready to go. Right, so it depends on how you do the bookkeeping, or
Yeah.
how long it would take them to come back, and it depends on the capability you have, and
Yeah.
or how long it takes to stand up capability, right, if you had to do a rescue.
One would certainly imagine that something like Space SQ Starship would be sitting there field and ready to go at any time, something that was single stage back to Earth.
It's not technically not
Wouldn't the
possible.
lunar gateways speed that up a lot too, that they're planning?
I don't know. I mean, once you get off the moon, most of the energetics to get back to Earth, you would still need a re-entry vehicle at Gateway. So I don't know that you can gain that much. I don't know. It's not
Right,
clear.
once you overcome the gravity well of the moon.
Then it's getting back through the atmosphere. That's the hard part.
But it's more about what did you pay for up front, right? What did you pre-stage, what capability did you build in? And then the other thing is you can have some compelling medical issue, right? I mean, I think I've seen on specials on television, right, that there's women with breast cancer, or people who, you know, there's the issue of what if your appendix ruptures, or.
Two years in a row, it was a doctor who
You know, when you go to Mars, should you have to take it off? Because of this medical issue, should everyone's appendix be taken out before you go? Because as a precautionary measure. So there are a lot of ethical questions, right,
Yeah.
that have to be asked.
Yeah, and so you can see why sending our undergraduates is a pretty good practice. I mean, even South Africa is a challenge at times, to be perfectly honest.
I think Stanford noticed that I sent a undergrad.
Yeah, I can tell you that, really, I was impressed.
Yeah, I was actually gonna chip in something regarding Mars. I mean, I think one of the major problems with evacuating from Mars can be your launch windows, because if you're not lined up in the proper, position of Earth relative to Mars, you're out of luck.
Right.
If all you can afford is a home in orbit, then you are stuck, as you say. I kind of think by the time we're really doing this, we'll have the capability to beat home and transfer by a bit. So it may not be quite as bad as you say, but definitely there are restrictions. And I'm not, given how long the timescale for evacuation is with any reasonable boost, it's not clear that's a real solution on anything. I think you're kind of committed once you go. Which is why maybe the moon is a great place to learn how to do this kind of stuff. Other questions or comments? Yeah.
Everything that you and Steve were talking about?
Oh, maybe not everything, but I think I got the main things.
The main points.
Did I? I don't know, Steve. What would you say?
I think you did great.
All right.
You talked about psychology, you talked about precursor on a chip, which may lend itself to
Maybe.
first steps.
We could consider it, yeah. I think there was a question over here. Yeah, a comment.
This mirror that you speak of, you're throwing atoms up and having them come down and bounce the light off that. Can you describe how you'd actually build that? Do you have to pull vacuum on these ice?
Oh, definitely. So it's a very high vacuum system, and the atoms are actually in a coherent state. So when I speak of atoms, really what you've done is you've entangled the wave function of a large number of atoms, so you interact coherently with a large number of ones. A single atom doesn't work, because if you try to bounce a photon off it, it kicks the stupid thing. And so, the recoil from it makes it not a stable mirror. Now, you don't need so many atoms as a macroscopic chunk of glass, but you do need a decent number together. And so they make these so-called Bose-Einstein condensates. And those Bose-Einstein condensates can be used for many different kinds of free fall experiments. But the virtue of this is that, that the longer that free fall path, the slower a wave you can study. And that turns out to be pretty important for exploring the spectrum of gravitational waves. And that's why a 10-meter tower doesn't quite do it. I mean, you throw them up and it's back down in a few seconds. At a few kilometers, then you start to get to the point where it's really attractive. Ultimately, you want to go to space to do this, because then you can fall for months at a time. But yeah, it's an atom interferometer, essentially. And like I said, it's right over there in the very comment. Yeah.
I have actually the same question about how you pull a vacuum in a 3-kilometer ice tunnel.
It wouldn't just be ice. You would almost certainly have to drop a stainless steel tube down. And one very important question that I've started to think about is apparently, so this program that I mentioned before where they're looking for neutrinos, what you drop down is literally a string of phototubes. It's not a rigid thing. And it turns out the ice actually flows around those phototubes on a surprisingly short time scale, at least surprised me. Yeah. So it's not like it's a rock that's static, but it does provide, the strings don't really slip that much. And so you can imagine something, if it was strong enough, that let the flow go around it. But it's not clear that that's going to be beatable. That may distort these or stress these arrangements to the point where you couldn't hold a hard vacuum like you need to for these sort of experiments.
The petroleum industry probably figured this out.
Sorry?
Yeah, the petroleum industry has technology to do this, like deep wells.
Yeah, but through ice, not so much.
Really?
Yeah.
Wait, so if you're using Bose-Einstein condensate as your mirror, wouldn't the whole tube have to be cooled to cryogenic temperatures, like Kelvin above absolute?
Absolutely. So the real reason for the vacuum is in some sense to avoid any interaction heating these things up. So absolutely. The very first thing you do is that the atoms are cooled down to very low temperature so they condense. And then you take this pool of cold atoms and you kick it with a laser beam, given enough momentum from a set of photons that you throw it upwards. But from then on out, if you're not kicking it vertically, it's essentially in free fall, except for the poling photons that you send in and out to check the position. So yeah, it's very cold. Makes Antarctica look balmy.
Do you have to coordinate between the different ice tunnels that you were talking about?
So you would have to have laser beams acting as a transmission between the tunnels. So you would have to either bring up the light on the surface and then phase reference it back down, or, and I don't know how one would do this, you would have to get evacuated channels under there. It's not clear that the scheme is worth the extra work, but the point is that people are trying to do this, are talking about doing this in rock. In fact, there's a schema that's trying to do something, or has proposed doing something similar to this in China. And there's no question that you can dig such holes in rock, but it's expensive and it's difficult to place them optimally. And there's another issue which is a little more subtle, and that is that it turns out the main background for this kind of gravitational waves is the fact that when a gravitational wave comes by, what it fundamentally does is it takes two of these mirrors, if you wish, and changes their relative separation. But there's other ways to move a mirror. If you have suddenly a mass that appears somewhere, it'll pull on one mirror that's closest to it and less on another one. And that's gravity doing that change. Well, it turns out that whenever you have seismic waves underground, you take little compressions and rarefactions in the background medium. And that effectively makes moving masses, very tiny but still significant, moving masses underground that are pulling on the mirrors. This so-called Newtonian noise turns out to be the dominant source of noise for these experiments. One great virtue of ice is that it's ice. It's essentially perfectly uniform. Once you get below the firn layer of about, well, there's a layer at about 600 meters when you stop having many of these bubbles. I think that's really the limit on the kind of studies that Xiaolin was talking about. The pressure becomes large enough that you actually get rid of the gases and the ice becomes very clear and relatively solid. Down in that layer, its density is almost completely uniform. And so the perturbations of the background waves make no difference in the density, essentially, except for small compressional effects. So that may help a bit. But this is it's a scheme, not an experiment yet. So, okay. Well, thanks for listening, and I think we're ready for our next speaker.
Yeah, that was great, and I think we're very fortunate to have the astrophysics introduction presentations by Dr. Wechsler and Dr. Pogue, and a broader explanation of some possibilities for Antarctica and human factor considerations from Roger, Professor Romani. And now a little shift. We'll hear from engineering. Henning Roedel, a recent PhD awardee from Stanford Engineering and Civic Engineering. And Henning, also a great supporter of the Stanford On The Moon Alumni Club, much appreciated. And we'll be talking on the rethinking of construction for Antarctica and the Moon.
Yes. All right. Thank you.
Pardon me while I set up slides here, but while I do that, I'm going to hand around a sample of our mooncrete, which is something we are developing here in the civil engineering department. I'll pass this around. This is one of the test specimens that survived our micrometeorite impact testing experiments. So,
What was the word?
mooncrete. Concrete. Yes, like concrete. Yeah, but well, I'll talk about it a little bit in my discussion here. Make sure the computer doesn't die while I'm presenting. And so my talk is really geared around the possibility of studying construction in extreme environments. Really, my PhD work formed out of this interest. Originally, I tried to do research in the Arctic regions and the Antarctic regions, but no one wants to build down there because it's too expensive and they all lose money. So we're working on that. So in the meantime, I had an opportunity while I was here at Stanford to study construction on the moon and in part develop a new type of concrete because, as you might imagine, shipping bags of concrete or shipping dirt up into space also not very economical. So maybe if I can get a hand, hopefully that will, so there's a screen here. It's up on the TV, but that's too small. Which one here?
That's
The reason I didn't put a presentation, I don't know.
supposed to work.
The tech was sitting back there with me, he's like, I don't know if I can help
Yeah,
you.
it's
I
a
might be
share
needing
right
to."
here. so-
Great.
That's a share. That's a share.
All right, well, we'll try without slides then. It is up on the TV here. Hopefully that works out. So, hi, I'm Henning Roedel, and I recently completed my PhD here in the Civil Engineering Department. And I've been interested in Stanford on the Moon since I heard about it. I'm passionate and excited about building in outer space. I hope my career can take me down that path one day. But in the meantime, I've studied. I've studied construction. I'm currently working in industry. I'm the West Coast Innovation Leader for DPR Construction. DPR is is the 10th largest builder in the United States. We do about $6 billion in construction annually, and we're very passionate about innovation. So the CTO is aware of my interests, and they're okay with it. So that's a plus. So if you think about construction and how we can actually deliver facilities, infrastructure, there's really three ways, right? There's in situ construction, which is probably the most common form of construction here on Earth. And that's labor, equipment, materials, resources at the site of construction. And that's useful for scaling up, right? Large buildings, large facilities, the work is done in place. That can lead to benefits, like scale, but also problems like waste, right? Most of the resources we have are productized, meaning you have to cut them, shape them, form them to your final configuration, and the scrap is usually thrown away. There's also modular construction, which is starting to gain traction in large part because there are labor shortages in the industry, plaguing the industry actually. So modulars kind of solves some of these issues of resource deprivation because you're doing the work in a factory first. You're building modules and then you're just assembling those on site. And that's beneficial for waste, that's beneficial for resource utilization, as well as you don't have an environment that can affect you, right? You're building in a factory versus building out on site. And that also allows for scale, right? You can assemble as many pieces as you want, and you still can have large-scale facilities. And then finally, you have pre-manufactured facilities. These are usually on Earth found in Antarctica or extreme environments, but also extreme environments such as refugee camps, where we need a lot of facilities in a short period of time. And so what you can think of in terms of pre-manufactured is it's all there in one spot. And because of that, because of the logistics of having to ship this pre-manufactured tent, facility, home, whatever you want to call it, you're limited by size. So that's one of the constraints there. But in terms of erecting things quickly and having it in place, pre-manufactured is actually a very good way to go. So as I give this talk, think about these sort of three construction types. And then I'm going to discuss a little bit, I'm going to go into detail about some of the constraints that we actually face in engineering and facility planning and management. Now, these are not all of them, but these are some of the ones that really are striking for remote environments. And that's logistics, getting your labor, equipment, materials out to the site. There are legal restrictions, right? And I'll discuss a little bit about that. I'm not a legal expert, I do not claim to be a legal expert, so take that with a grain of salt. The environmental constraints, we've all heard about a lot of the environmental constraints in Antarctica, and they are similar in many ways, or analogous to the moon. And then what local resources we have available for construction. So these are just a few screen grabs or images I found of construction activity in Antarctica. So we've been building in Antarctica since about the 1930s, 1940s. And you'll see, there are examples of all three types of construction that I discussed earlier. There's in situ construction. Down there's a wharf being built with equipment, labor, materials, going to work and being built in place. But there's also examples of modular construction, right, where you have modules that were assembled. I think that's the Haley 6 research lab from the British Antarctic Survey. You have these geodesic domes, which were a fan favorite for a few decades, which could be assembled. And then, of course, you have the homey igloo, built with local ice resources. I know it's kind of hard to see with the lighting here, but that's an igloo. But then you notice also the logistic issues that we have to overcome, right? Equipment is brought in on tanker ships. Those tanker ships have cranes on the sides of them because there are no wharfs or ports. Maybe at McMurdo, I've never been to Antarctica, so maybe my esteemed fellow presenters who've been can confirm or deny that. But heavy equipment has to be all planned, fit onto a cargo container, and then lifted onto the ice shelf before it can even do work out on the Antarctic ice. Airlift has been a common way of bringing out construction materials and labor, and then just snow trains, bringing the fuel, the food, the screws, the hammers, you name it, the welding gear, generators, all of that is needed in order to construct a facility in these remote locations because power is not there, and the fuel obviously can't be harvested from the ice. So there's a lot that goes into Antarctic construction, which makes it an extremely valuable place to perform research on how to build, perhaps maybe on the moon one day. So if we look at a little bit to the future and we look at the moon a bit, lunar logistics is actually a really big problem, right? We don't have the capabilities, as far as I'm aware, to actually get to the surface of the moon today. We have technology that we have to spin up and build, and I'm looking at Tammy here if she knows anything more than I do. But these are some examples of past landers, future concepts for a lander. This is the Blue Origin. I think they're calling it the Blue Moon Lander. And you'll notice actually there are cranes, similar to the ships that go to Antarctica. So we're starting to see some analogous concepts. And then, of course, for smaller landers, you have the rover kind of on the side of the lander there, and that drops down, and then the rover can explore the surface of the moon. So this is just the beginning, and the way in which we build on the moon will really be based on how much we can actually get down to the surface in terms of labor, equipment, materials. Now there's also legal considerations for construction. Just as we have the Antarctic treaties and the environmental protocols, I think it's called the Madrid Protocol in parlance, but it's basically in the 90s, the consortium of parties to the Antarctic Treaty came together and they decided, we need to protect the environment of Antarctica, we need to protect the flora, the fauna, but we need to protect it for future generations. And so many facilities, since this protocol was enacted in 1998, are actually designed to be removed from Antarctica once they are at the end of their useful life. So they can be disassembled, shipped back out to the mainland countries, and you don't have these artifacts, these man-made artifacts left in the ice sheet. Because after every winter, snowdrifts actually cause many of these buildings to sink, and they have to be dug out and brought back to the surface. So you'll start to see in some of the newer buildings in the research stations in Antarctica, they're all on stilts. And the reason is because after the winter, you have to raise those stilts out, fill in the snow underneath, and then place them back on top. Otherwise, they will eventually sink into the ice sheet. So these are also considerations, perhaps on the moon. we don't really have ice, snowdrifts on the moon. I should qualify my statement there. We don't have snowdrifts, but we definitely have meteorite impacts. We definitely have meteorite impacts and other possibilities for the environment to affect our construction. So a big one, and I think we've heard about it in terms of the psychological impacts, but this is also a big one in terms of having the energy and the ability to actually build, is the daylight that we have on both Antarctica and the moon. So the top graph up there is the daylight profile for the South Pole station. So that's a 12-month period along the bottom there. And areas in yellow is when you have daylight, and areas in the dark gray are when you have no sunlight, the winter over period. And the bands in between are when you have periods of weeks of daylight and weeks of nighttime as it's transitioning to the full summer or full night. So similarly on the moon, if you're not at one of the poles, excuse me, you'll go through a day-night cycle. And that day-night cycle is 14 days each. And so that can have significant impacts. If you do not have sunlight, you have to think about a different source of power on the moon. Right? You're not going to have solar, you're going to need nuclear, you're not going to be burning fuels because there's no readily available oxygen unless you're harvesting it from the soil. And so also with those day-night cycles are large temperature swings, and certainly much larger temperature swings on the surface of the moon. But that also depends on your materials that you're using and how well they absorb the radiation and how well they reflect it. And so it gets complicated. And those are all planning considerations for when you're bringing labor, equipment, materials to build your facilities. There are also varying ground conditions. I spoke about the ice in Antarctica, but on the moon you have this soft powder that's very abrasive. It's also statically charged because of the solar wind. It likes to stick to your clothing, likes to stick to your vehicles, and then if you have any moving parts, that abrasion and glassing material is actually pretty harmful for that equipment. The lack of an atmosphere on the moon makes it very interesting to work in. Obviously you have to protect your equipment. If you're working with most of our construction in terms of concretes or ready mixed materials involves some sort of water or solvent. And so without an atmosphere, you're going to have to figure out how to actually work with that material or come up with a different way of solidifying materials. And of course you have radiation and meteorites from the environment. So I spoke a little bit about meteorites at the beginning of the topic. I'll go into a little more detail. But just in terms of the radiation, on the moon, on the surface of the moon, you have to protect yourself from galactic cosmic rays and solar flares. Those are the two extreme events. And in order to protect yourself, estimates range about 2 to 3 meters of material are needed to protect you from those extreme particle events and having cascading reactions throughout the material before you're protected. I can go into more detail there, but essentially, if you have a neutron at high energy hitting some of the regolith on the moon, it has been detected to cause nuclear reactions that cascade down. So that's what we need to protect our astronauts and folks from. So, and I'll defer to my physics colleagues here. I will say I did not take a physics class at Stanford. I went to UCLA, go Bruins, but I'm also a Stanford alum from the graduate program, so I'm happy with both schools. So that gets me to the last part, local resources. So if we can utilize some of the local resources at either of these locations, we're much better off. That solves a lot of issues around logistics, around the environment, because those materials are stable in that environment. And so there's some real benefits there. You do have issues when it comes to building locally and in situ, so it's a trade-off. It's all about planning. But that's something that we studied here at Stanford, and we took a long look at various ways of actually combining or sintering or cementing the lunar regolith, which is the soil on the surface, into workable material. And so I give two examples. Both are robotic. I think the opportunity for the moon and using robots is paramount. And the first uses a laser to sinter from the surface. So if you have a nice smooth surface, maybe you can trowel it or scrape it so that it's smooth. Then you can drive over and sinter the surface and maybe create some tiles or even a road or landing surface. Again, that's an energy-based method, so that's going to require quite a bit of energy, but it's not going to require any material binders. Next to that is a 3D printing method, and for most 3D printing or additive manufacturing methods, you're talking about the use of binders, right? Cements, epoxies, anything that you can sort of encase the lunar material as a volumetric filler with some sort of binder. And so additive manufacturing is another promising technology, and there you need to mix the lunar regolith with a binder. But you don't have to think about just facilities with these methods. You can build tools, gears. Your engineering imagination is your only limitation there. So what did we study here at Stanford? How did we sort of combine a lot of these ideas and come up with our concept? Well, we actually worked with the NASA Ames Synthetic Biology group. The idea being, if you can grow food, perhaps you could grow your cement. So, and if you think about that and you scale that idea up, it would require maybe a test tube of engineered microorganisms, or several test tubes brought up, incubated, and grown on the moon, but then you have a ready source of binder, and of course you have a ready source of aggregate to mix the two. So anyways, that's the going concept, and what I've passed around, and I'm not entirely sure where it is in the audience, but my wife is holding it, thank you, is you can combine the regolith, the protein, a bit of liquid water, and if you let the water sublimate or evaporate, it will harden, and harden into, in fact, a very strong material. We're talking on the order of ordinary Portland cement. That's about 30 megapascals of strength. So very, very strong material. It really benefits from the small particle size of the lunar regolith. And then we're taking that a bit further. So now we have this material, we've characterized it, we can engineer it. We have mixture design theory, we have strength design theory. So we're starting to look at how does the material interact with the environment. So the first, of course, and most exciting is meteorite impact studies. So the question being, if we know how big a landing pad or a facility would be, how long would it be until many micrometeorite impacts would reduce the structural integrity of that structure? And so it required characterizing the response of our material to meteorite impacts, and then modeling lunar meteorite flux, and then using a theory developed here at Stanford by one of my colleagues, actually coming up with a design framework to design how thick your tile should be, how thick your roads and landing pads should be for a 20-year period. The answer, in case you're wondering, is about 4.5 inches thick. And yes, we use inches. We're in construction in the United States, I apologize. So just to kind of wrap up the talk, there are a lot of constraints, there are a lot of benefits, but the analogs between Antarctica and the moon, I think, warrant more study and give us an opportunity for Antarctica to be a laboratory for construction research. If you think about it today, the way in which we build is not applicable to outer space. We have to change the way in which we build. It involves technologies, it involves considering these 4 factors among many other, economics being another major one. And so we have to change, we have to innovate. And what better way than in a place like Antarctica, where the conditions and the environment almost force our hand to change the way in which we build and give us an opportunity for innovation. So that's my talk. Happy to answer a few questions. Yeah.
So I've heard people discussing schemes of solar centering on the moon to avoid the energy problem. Have you guys looked at that at all as a path? And any comment about what you think?
Yeah. So there have been a few studies, one from NASA, and then ESA has been pursuing this quite thoroughly. The issue with any sort of sintering and additive manufacturing is the adhesion between layers. And so with solar sintering, you can get that first layer nicely sintered, but then getting the second layer and subsequent layers becomes difficult and a real engineering challenge.
Is it worse than laser sintering for some reason?
That's a good question, and I'm not too familiar. I think with
free
laser
power.
it is free power, absolutely. With laser sintering, I think you can control a bit more what energy you give to the particles, but I'd have to dig into the research a bit more. But I've known both with laser and solar sintering, you have adhesion issues for larger objects.
Did you tell us what centering means?
Oh, yes. So sintering is the process of taking particles, heating them up to a very high temperature, to almost their melting point, and that causes the surface of the molecules, because of a heat differential, to start to melt, and they can fuse together, but then cool down afterwards and be a solid surface. So instead of the difference between sintering and just casting is that sintering usually leaves behind a porous structure, and not as strong as a purely cast or 100% melted production method.
Did you use actual regolith from the moon to do your concrete samples?
We try.
And if not, what did you use? And why is it a standard?
Yeah. So obviously we don't have an unlimited supply of lunar regolith yet. And so in lieu of that, there are simulants that are similar in particle size distribution, chemical structure, that are sourced from volcanoes here on Earth. So the sample that was passed around that's made from JSC-1A lunar regolith simulant, JSC standing for Johnson Space Center, was managed, the production of that simulant was managed by the Johnson Space Center.
And 1A means it's the very best.
1A is the top, I guess.
But the very fact that you're saying it's a simulant had to have been based upon some lunar samples coming back.
Correct. Yes.
I'm an undergraduate here, and I'm part of the Stanford Student Space Initiative,
Yeah.
and our Mars team, which is formed over the summer, is not just on Mars, but also on human habitation on the moon, is actually working in the Bloom Center with biopolymers, and is trying to work to create a project related to production of bricks in an automated process. And I was wondering if we could pick your brain about it, if we could
Please,
put you in
absolutely.
contact with the leader of this group.
Yeah, I think we spoke on the phone maybe in February with the leaders of the group. I'm glad I'm making progress. Yeah, happy to continue that conversation as much and as often as I can.
Thank you.
My understanding is that the moon regolith is full of helium-4. Is there any chance, is there any discussion about trying to harvest the helium-4?
Of course. I mean, there are lots of discussions about mining and basically creating an economy on the moon so that we can continue our efforts for scientific research and tourism and all the other things that go along with construction. Personally, in my career, when we get into construction in space, I think the very first activity that has to happen is we need to have some exploration on the surface of lunar resources. I do think that water will probably be the first mined material on the moon.
Yeah, so that discussion is ongoing, right, because it's so expensive, meaning the up-mass capability, right, is you're limited in up-mass. And so if you can't live off the land, it's probably not sustainable.
It's going to be very expensive. You're going to need more tech billionaires.
Send them all there.
Yeah.
Even if you can get water from lunar ice and use lunar regolith as your raw material, you said that you're going to grow the binder through biological processes, but you're going to have to continually send more of that to the moon ice.
Yeah. Yeah.
What about the planetary protection concern?
Oh, yeah. So with the moon, it's not as critical with the moon as it is with Mars and other places where we are really searching for life. However, the one thing I didn't mention in the legalese is that the Outer Space Treaty, which the United States is party to, has planetary protection clauses. So, but if we're sending humans and we're trying to start a colony and we're bringing food and we're trying to grow food, we're going to have to rethink, I think, those planetary protection clauses and what it means. But absolutely, it's
just something you would have to navigate.
Yes, absolutely.
But getting back to my question, how does that affect the economics of making this stuff on the moon if there's still a raw material you have to send lots of?
It's a very good question. And right now, I'm holding out hope that there are raw material stocks that we can leverage on the moon. But I don't know enough about the chemistry that it may not be a winning idea. It may be that we have to go through sintering and energy-based methods. But I still think what we're doing is an opportunity for very exciting research and to push civil engineering into a new direction. I mean, here on Earth, we use cement. We use cement more than any other material other than fresh water on Earth. We're not going to get away from using that. And so the opportunity to study other binder systems, I think, is a great opportunity. We might not, find the material, the better cement in our first, second, third trial, but eventually, as we keep trying, we keep thinking about these extreme environments, I'm hopeful that we can find new ways of building.
But you're only at 1/6 of G,
Yes.
so that's helpful.
That is helpful. And in fact, I mean, most of the designs that I've seen are really actually for radiation protection. That 3-meter thick shell is your driving construction constraint. It's a lot of material to move, and you don't actually need to bind all 3 meters. You just need some sort of form or shell, and you can pour in the material. I actually imagine concrete in general is not strong in tension. So if you have a pressurized module or habitat, the concrete's not the material of choice. You want to send a habitation module. Yeah, go ahead.
So, in terms of getting materials to the moon, I mean, if you could smelt asteroids to supply the metals you need, now there's another harsh environment for developing.
Absolutely. And there are materials. I mean, there are metals in the lunar regolith. I mean, we have lots of meteorite impacts there, so there could be resource veins. So there are a lot of possibilities. But again, we need to actually do some physical exploration. I think that the satellite-based methods that we have right now can only penetrate so far into the surface.
2 questions, actually. Number 1, what are your thoughts on underground construction on the moon?
So that's another possibility. And there are lava tubes on the moon, so that could be a nice, easy place if we can safely traverse into them. Then that's an opportunity that avoids a lot of the construction logistics. So that's a good one. Digging deep into the surface of the moon gets tricky after, I think it was 10 to 30 centimeters, something like that. When the Apollo missions were drilling, most of the drills got stuck at that depth, and it was partly due to the compaction, partly due to the particle size, and so it will be a challenge.
And second question was, you mentioned something about building landing sites with your concrete. The immediate concern I have there is heat from the rocket exhaust. How does your concrete withstand that?
We need to do an experiment to find out. You're absolutely right. So to that point, there's a research group in Hawaii, PICES, the Pacific International Center for Space Exploration.
Exploration
Systems, thank you. Partnered with NASA and Kennedy Space Center, and they actually had a tile casting system. So they used volcanic rock from the local Hawaiian Islands, cast those into tiles, had a robot, actually a rover, lay those tiles down into a landing pad formation, and then fired a model rocket engine to simulate rocket plumes, and it did not survive. And so the state of the art needs some help. Last question, yeah.
What are your thoughts on the potential for this concrete to be used on Earth and create more environmentally sustainable forms of concrete? Do you think that it's economically feasible? Do you think that it's technically feasible?
I wish. Otherwise, I'd be pursuing that. Unfortunately, our material in its current form, if it gets wet or is submerged in water, the protein will disassociate from the regolith, and you've got a big pile of mush. So it's not really feasible here on Earth yet. There's probably some engineering you can do to prevent that. But in the meantime, it's an exciting opportunity to pursue this research. Thank you all.
Thank you, Henning. And it's great that there are so many, it's just like a Stanford seminar here, so many interesting questions, and we've used up all our time. I'd just like to make a few concluding remarks. This is the 100th anniversary of the International Astronomical Union, which I'm a member, and we applied for recognition by the IAU for this event to be included in this centennial year for the IAU, so we can regard this as Stanford's participation in the IAU centennial. We've been conducting, last year, we had our International Lunar Observatory Association, which is hosting one of its many Galaxy Forum scientific outreach events. We're hosting a Galaxy Forum in Hainan in February. That's China's Hawaii Island, they call it. And we have a competition, an essay competition for first woman on the moon. What is the significance of the first woman on the moon? And now that there is a commitment to do that, it makes the question even more important. I happen to think that the landing the first women on the moon in the 21st century will be as influential and important as the landing of the first men on the moon in the 20th century. Why not? And the prize for this competition is a full expenses paid participation in the Galaxy Forum Hainan 2012 in February. There are a few brochures describing the event upcoming in the competition in the back of the room. As far as Stanford on the Moon goes, next year will be my 5-year cycle, times 11. It'll be my 55th class reunion, also the class reunion of the class of 1985, which includes one of our first and most active advisory committee members, Grant Anderson, who's president of Paragon Space Development Corporation. That class also includes a gentleman named Mark Armstrong, the son of the legendary Apollo 11 astronaut. And those of you interested in attending, I hope you have signed our sheet, and we'll be sending out information about next year's Stanford on the Moon Alumni Reunion Conference. And finally, I'd like to thank very much the great presentations from Risa and Kelvin, Roger, Henning. Really interesting. I found it very stimulating, as many of you did with all the questions you had. I'd like to thank the chair of the physics department for hosting us once more, Dr. Shami Katru, and ask Shami and the physics administrative director, Rosanna Yao, and her associate, Jennifer Tice. If Jennifer is here to come up, we have a little something that my associate, the Beagle boy, in the back of the room, has to present with me to Shami, and Rosanna and Jennifer are here, and all the staff at the physics department. And this is the Beagle boy, my associate.
Nice to meet you
Well, she is. Maybe we should give Rosanna a little heads up, but they've been very, very hospitable, professional, effective in making this event happen.
I have a comment.
Yes, Barbara.
Yeah, I'd just like to emphasize for everybody the importance of the legal aspect. I'm a Stanford grad, 69, and also graduate school. And I worked in the Department of Justice. And on the Attorney General's legal review, which made it possible, we went to NASA and we made it possible for women to be allowed into the astronaut corps.
Thank you. I know Stanford especially is very, very happy that that was done.
Right.
So for the hospitality and organization that Stanford Physics has done, we'd like to make this presentation a nice award to this, presented by the Stanford On The Moon Alumni Club for the Physics Department Appreciation for hosting the 2019 Stanford On The Moon Conference, 25 October 2019. Shamit and Rosanna and Jennifer, you want to share this? Okay, well, thank you all very much and have a great reunion weekend. I hope we can come back to Stanford On The Moon events in the future.
And the reception is also.
Yes,
thank
you.
Oh, there's a reception?
Well, the physics part. You're welcome.